All right, so answer the first one. What do we got?
Huh?
Nucleus.
Okay. Major difference between alpha, beta, half from gamma. What do we got?
Um, Gamma is larger?
No,
No?
that
Gamma's
actually
like
doesn't even make any
light.
sense. This is light or energy.
Yeah, but the
No,
lengths.
no.
Oh yeah, because that's smaller.
So what are these
These
things
are
over here?
particles.
These are
They're
particles. These things over here are not energy. Can they cause problems for you? Absolutely. But the alpha and the beta are actual objects that have mass and volume, and in this case, charge. And the gamma is light. There's nothing there. It's just energy being transferred. So if you're irradiated with gamma, and then the gamma radiation turns off, and then you turn and hug somebody, did you just put gamma on them?
no.
No. In the same way that if you're standing in front of a light bulb and then you turn the light off and you turn around and hug someone, you don't put light on them. But if you're irradiated with alpha and beta particles, they're things that are now on you. And so then if you turn and touch somebody, then you can pass that radiation on to them. You okay with that?
Yep.
Isotope.
An isotope is like uh the same element of something but with a different number of neutrons.
So there's two ways you can think about it. You can think about it as a single atom. So this atom of carbon has a mass of 13. That is an isotope of carbon. Or you can say, I've got a carbon 12 and I've got a carbon 13, and they're isotopes of each other. So either way you want to do that, that works. What does 20F9 tell you about this isotope?
Um
Extra neutrons? Two extra neutrons? No, I think it's actually one extra neutron off of normal because isn't it 18 point like 99 something or other? Yeah, 189984. All right, so what kind of radiation has an electromagnetic, or what kind of electromagnetic radiation has a wavelength of 5.5 times 10 to the negative fifth meters? Did you guys look that up? My guess is you could have gone to the notes.
It's somewhere in between radio signals and microwaves, if I remember right.
Sure, maybe. Let's see. And then gone to this guy right here. This isn't the most accurate, but it's times 10 to the negative, it's times 10 to the negative fifth, right?
mhm.
Five. Sorry, could somebody read the number?
I think it was 5.5 times 10 to the negative 4.
Okay, so 10 to the negative fifth is right here. Okay, so 5.5 times 10 to the negative fifth, that's going to be somewhere around right here. So that's definitely going to be infrared radiation. Okay with that? Because this is my wavelength in meters. Oops. Okay. So this should be infrared. Okay. What has more energy, blue light or green light?
Blue?
Blue. How do I do this? How do you know that?
Because of the charts.
Because of the chart? Great. Any other way? This is the rainbow, right?
Roy G. Biv.
What's right here?
At the end
that
of the
kills
rainbow?
you.
On the outside of violet, past violet. Super easy.
Ultraviolet.
That's UV, right? And then what's over here? On the other side of red. Super easy.
Infrared.
Infrared. Which one of these two things will cause cancer?
Ultraviolet.
UV.
So that one has more energy. And blue is closer to UV, so that's how you know it's got more energy in it. Okay with that? Also, I know this is a stretch for your age group, but has anybody ever done actual photography with film? Okay,
I have a Polaroid.
Yes,
that doesn't, Polaroids don't count.
room in every
Okay, so what color is the light in the,
red.
why is it red?
I don't remember. I failed that class.
Okay, but look on this list here, this Roy G. Biv list, and tell me why red works and say blue won't.
It doesn't expose the film, right?
This has, oh God, I always forget that thing's fat. Less energy here. So the red light has so little energy per photon that it can't actually develop the film, the negative for you while you're doing the developing. But it gives you enough light to wander around and not bump into stuff. Write down all three types of annotation with a potassium with 22 neutrons. Okay, so I've got a K, and it's 19, and 22 would be 30, 41. Okay, so there's type 1, there's type 2, and there's type 3. That work? What's missing in that first equation?
The carbon afterwards.
Isn't it?
It's not a
nitrogen?
carbon. Yeah, so there's 14 here, and the number up top has to equal the same on both sides. So it's 0 for this one, so I know that this guy has to have a mass of 14. This number is a 6, and this over here has to add up to 6. So this has to be a 7. 7 plus minus 1 gives me 6. And so then what has 7 neutrons in it? A nitrogen. That's how you do the math on those. Okay, so the second one's even easier. What do I do for the top number, the mass number?
Add.
Just add them up, right? This is 228, and then the bottom one is just 88. And what is that?
Is that radium?
Radium. Yep. So if I was a radium atom, I would undergo transmutation by shooting an alpha particle out of me and then creating radon gas. What needs to happen for radiation to give a person cancer? What do we need here?
It needs to like interrupt while the DNA is like replicating, and then if it's like a non-benign, screw up, then you get cancer.
Okay, there's one thing I want you to say there. One extra thing, like really important thing.
It has to have an energy over 10 EV.
Did you say tiny V?
10 EV.
10 EV. Oh yeah, 10 EV. Yep. So the energy must be able to break a chemical bond. I'm being specific with chemical bond because I'm not talking about intermolecular forces. If the intermolecular forces can be broken by lots of things. Infrared can break intermolecular forces. Light can break, like visible light can break intermolecular forces, but that's not going to give you cancer. What's going to give you cancer is I break a chemical bond, and this happens during mitosis, while the cell is separating, while the DNA is exposed. I suppose it could also happen during DNA replication. All right, let's go mitosis and transcription. Do you guys have enough biology in you to know what transcription is?
No.
Yes.
How many yes?
I'm taking biology next year.
The DNA needs to be read. The DNA doesn't do squat. It's actually like a book. A book doesn't do anything. Well, I guess it could hold up a table, but a book doesn't do anything for you. It just has the information for you. So DNA is like a book. It can be read. While it's being read, you could damage a book, right? Like somebody could drop Coke on it or something like that. So the same thing happens with DNA. If it's unwound and being read, then some bad stuff can happen to it. So the DNA, that definitely happens during mitosis, and it definitely happens during transcription. So if either of those things happening, then the chemical bond that can be broken can be one of those nucleotides being broken.
So specifically during mitosis, it has to break the chemical bond?
Yes.
Okay.
The other part about this is the cell has to live. So usually what happens when the cell gets hit like this is the body recognizes it and kills it. It's when it doesn't recognize what's happened to it and it allows to replicate that bad things can happen.
Doesn't it like tell the cell to kill itself?
Yeah, but it has to go in and be like, hey, sure. Basically it sends a bomb. Or maybe sends the instructions for a bomb, and then the bomb is assembled and it kills itself. Basically just lyses the membrane. All right, fundamentally a neutron is what?
Nuclear.
Isn't it just a proton with an electron like in it?
It's a proton with an electron basically attached to it. So the proton is a +1, the electron is a -1. When they come together to form a neutron, I get no charge, which is the source of your beta particles when they come out of the nucleus, which was this example right here. Carbon-14, which is radioactive, releasing a beta particle. So this neutron loses its electron. So now this thing is gone. And now I've got a plus charge. So I went from a +6 to a +7, and I made myself some nitrogen. Okay. Any questions about this? Are there any annotations that need to be made? Okay. So what was the most important part about this?
The homework?
No, about this electromagnetic spectrum that we were finishing. Last thing we talked about on Tuesday. I'm actually purposely picking this. This guy. Right here. This line is the most important part. So everything over here can cause cancer. Everything over here, no cancer. And remember what is over here. What is the stuff? Like, yeah, we know what infrared is. Yeah, we know what microwave. But these radio waves encompass what common rays? What common radiations that you're being exposed to constantly? Obviously.
Or AM.
Obviously AM and
waves.
FM, but people don't listen to the
cell
radio
phone?
all that much. Your cell phone radiation, absolutely.
And your
Your radiation,
Wi-Fi?
absolutely. The cell phone radiation varies. It's based off of which the frequency changes based off of which type of radio or which service you're using. Like US Cellular uses a little bit different technology than say AT&T does. All right, what else is inside of there besides cell phone radiation, radio waves, and and infrared. Sorry, and Wi-Fi.
Five G.
All I heard was G.
5G.
Yeah, well, that's cell phone technology. There was a great thing I saw about somebody saying, okay, so conspiracy theorists, 5G causes COVID. Okay, got it. Conspiracy theorists, COVID doesn't exist. Okay, you can't have it both ways. It's either it exists and it's caused by 5G or it doesn't exist. You don't get both, you don't get your cake and eat it too. How about,
Expect consistency?
right, yeah. The other stuff that's in there would be like walkie-talkies. They're not used all that much. CB radios, also not used that much, but they're definitely out there. Beeper technology, which you might think is gone, but it's not. Does anybody know why beepers haven't actually disappeared?
A buddy of mine's on the fire department. They actually use something similar to do out calls. It's literally a beeper.
But,
And it
but
makes
why do they have
calls.
that instead of phone calls or text?
He has it everywhere. I don't exactly know how it works, but like he's
It
got
works.
calls in the middle.
It works everywhere. The reason is it works everywhere. The wavelength that beepers run off of is longer, which means it can penetrate, which is why doctors have it. So if you're in the basement of a hospital, usually where the MRI machine is, and the doctor's down there and something bad happens with his patient, you need to get a hold of them, you can beep them. You try to call them and the cell phone won't ring down there because they're not getting good service. But the beeper will beep, period. It just works.
My mom's hospital does that. They have a little thing called a Vocera, and they just clip it onto their uniform, and it does that. It's pretty much a beeper.
And you've probably all seen that at restaurants, right? Like the line is going to be 30 minutes, you know, go wander around somewhere and then we'll beep you and you can come back and your table will be ready. So they're not worried about it not working. It's going to work. What else is inside? Oh, television, regular television, not cable. Like put up the rabbit ears and, well, it's not a rabbit ear anymore. It's like a panel, but whatever. Regular old TV. I'm sure
Is the satellite-based stuff in there too? Like,
No.
where would that even be?
it's in radio waves. Yeah, for sure. Okay. So just some ancillary information about some of these things. So radio waves, I mean, we know what those things are. They can be reflected in the same way light can be reflected. So everything that you think about light, visible light, that applies to all of these things. So if you're shooting a gamma ray gun at somebody and they put a mirror up, it's going to be reflected at you. Like that's going to happen. Some of it is going to go through, but it will be reflected at you. So everything you can think about with light also happens with all the other forms of electromagnetic spectrum. So if light reflects off of clouds, so you might have if it's a cloudy day or cloudy night and the clouds are pretty low, a city will be brighter than it normally is on a skyless night or a cloudless night because the light from the city goes up and hits the clouds and reflects back down. So that actually happens. And the same thing happens with radio. If you're in the city and it's a little bit cloudy, you can get better signal. The microwaves, it's just an interesting thing with microwaves.
Phenomenon.
So the hydrogen and oxygens go in and out like a slinky. Okay? There's also a little bit of rotational direction with this, but with microwaves, we're concerned about the in and out in and out slinky effect of the H's and the O's. Microwave, go ahead.
Are you saying like this is whenever a microwave
Period.
interacts with
A water molecule does this no matter what.
Oh, okay.
It's always doing this. The microwave just happens to be the correct frequency, which we would call the resonant frequency, to cause that to happen more.
More frequently?
Yeah, I mean, are we okay with the term resonance? We're going to talk about it a little bit today, but It's
Um,
you get that effect when you're in a room, like in a stairwell, like everything's concrete or something like that, metal, and it seems like you're talking louder than you are. The stuff's building up on top. So that's what happens when the water molecules get hit with the microwave energy. They actually just fluctuate faster. So they're moving faster. Well, a molecule moving faster, what do we say is happening to it?
it's gaining energy.
Okay. Like nobody actually says that though. What do people say?
Vibrating?
Yeah, but nobody says, "Hey, these molecules are vibrating faster." They say it's
Hot?
what? It's hot. That's it. The temp's gone up, right? So the reason that the food gets warm is you're vibrating the water molecules faster, and there's almost no chance that your food is water free, right? Plus, it doesn't just hit the water molecules. It just does that best. And you know that it doesn't just hit water molecules because I'm sure there's a cup or a plate or a bowl that when you put it in the microwave, that damn bowl is like hot like the sun, right? You can't just
Yeah.
grab it and pull it out. You have to use a hot plate. So some paints will absorb at that same frequency that the water molecules do. So the best thing to do is put in like glass Pyrex. The reason that gets warm is because the food gets warm and then heats the glass. But the Pyrex itself isn't really absorbing any of the radiation from the microwave, so it itself doesn't get warm.
I have a lot of ceramic bowls that just get super hot.
Yeah, well, that's what ceramic, especially the
Yeah.
paint on ceramic, the glaze on ceramic does. Um, infrared is just that region that is heat, or that we perceive as heat. It can't cause cancer, but it can certainly damage you. In the same way, I mean, light can damage you, right? We okay with that? Visible light could actually damage you. A laser is visible light that's concentrated. There's a part in the rebooted Batman movie where Christian Bale's Batman puts the mobster guy on a like a spotlight for planes in a shape that makes it look like the bat symbol on the clouds. All right, great. My problem with that is they cut that guy down and he was still alive. Tell me why he wouldn't be alive. I know incandescent light bulbs aren't really a thing anymore. You guys have compact bulbs and
Wouldn't
LED
it be like
bulbs.
really hot?
Yeah, it would be like 1,000 degrees. And I'm not joking about 1,000 degrees. That's what the temperature on that would be. So obviously that guy wouldn't just come down and be tired. He'd be dead. He would have been cooked because there's a lot of energy in that. Okay, so you're going to refer to this little picture probably, I don't know, 10, 20 times before we're done with this class because you're going to answer questions off this. This is the visible light spectrum. So between 400 nanometers and 750 nanometers, that's all we can see. That's it. I mean, it is a phenomenally tiny sliver of all the different wavelengths that are available from like 100 kilometers to picometer size. And this is all we got is this tiny, tiny little sliver.
Can
So
some animals see more?
barely, like maybe 780, maybe 340 or so 360, something like that, some of that range. But it's not like cats can see better. That's not why they can see better at night. They have different receptors and their cones and rods are set up differently, so they pick up on things better. And you could see things outside of the spectrum if we use technology. So like an infrared thing that maybe like you might have seen one in a like a video game, or maybe you've even put one on. And so what the infrared is doing is you have a detector that detects IR radiation, and then it converts it into visible light for you, and then you can see that. Which is why when you look through those, you don't get color because there isn't any color. It's just a heat signature. So anything that's warm would show very brightly, and anything that's not is not shown brightly. If you've seen the first Predator movie with Arnold Schwarzenegger, he lives because he coats himself in mud, and his entire body temp drops to the surrounding materials around him, the mud, the plants, and whatnot. And then the Predator with his infrared vision can't see him and walks right past him.
Mhm.
Watch the movie again.
Just don't use a gun.
Don't use a gun? Why?
Because then they feel threatened and then they are more obligated to attack you.
No, the predators won't hunt someone that's undefended, so they'll just pass you by.
Yeah, but of
exactly.
course he's
You're
going to
not a
try to
good
kill
sport.
Arnold Schwarzenegger because he doesn't need a gun.
I know he's got guns.
Exactly. He said that in an interview. That's why I said that.
Amazing.
Okay, so ultraviolet light, it's on the other side of visible, and the ultraviolet light itself is the first radiation that can cause cancer because it has the ability to break chemical bonds. And then we are spared from dying from this constant source of ultraviolet light because of the ozone layer. And that ozone layer we've talked about several times, protecting us from that. Then X-rays are smaller. Their wavelength is even smaller, and they have the ability to penetrate. But some things they don't penetrate well. So what is an X-ray not able to really penetrate well?
Uh,
Lead. Actually, light itself, all forms of light do a really bad job of going through lead. Period. Any of the types of radiation. Lead is a good way to shield from that.
is it because of its density or?
It's because of when we were talking about the crystal lattice structure of solids, it's
Yeah.
because of its particular crystal lattice structure. So other substances with the same kind of crystal lattice structure, like barium, have the same ability to be, it's called radio opaque because some of the radiation still gets through. So it's basically just blocking a bunch. It's like putting a curtain up. Like these curtains over here, I mean, like you can see light even though these curtains are here, but most of the light is being blocked. So that's sort of how lead works. But if you put enough curtains in front of your window, eventually no light's going to get through, and the same thing with the lead. And then same situation with the gamma rays. They will also be blocked by lead. So because of the fact that these X-rays, and more specifically the gamma rays, are basically just traverse through the solar system, there's nothing blocking them. They just run until they run into something. It's not going to be really easy for us to travel any distances. When people are like, just build a spaceship and make it big enough to have a bunch of food on it and send people to Mars. Gamma rays are a major reason why this is a problem. So what would you need to do to the exterior of your spaceship?
Lead, but that's really heavy.
There's your crux right there. I got to put lead on this, and lead's really dense. So how the hell do I get enough lead up into the space to use this? It's a conundrum that we're gonna have to fix. We're gonna talk some about that.
Is there anything else that can do that that's lighter?
The other thing that does that is barium, but it's not structurally sound. It's a crappy metal. And lead isn't a great metal, but it's also, lead doesn't oxidize, and barium oxidizes like crazy.
Yeah, but what if you had it like where it was your base metal, like what protects you on the inside, and then you did barium, like coated it in barium, and then you put another metal on top of that, like a thin, like each one would be pretty thin.
Sure. I mean, I'm sure somebody's thinking of these different ways to do this, but it's not. Wait, I keep saying barium, and what I mean to say is boron, not barium.
Boron.
Yeah, big difference. Not BA, just B.
B. Yeah.
I found this, and I just thought it was kind of interesting, so I included it. It's basically they've taken this spectrum right here and then made it fun. I don't know.
That's not fun. That's terrifying.
Well, when you look at it, see what's happening. If you start over here, if you start right here, you can see what's happening to this wavelength. It's getting shorter and shorter and shorter, right? As you spiral in here. And so as you move through this, you can see that, okay, so my UFV TV has got a longer wavelength than my VHF TV. And my FM has a longer wavelength than my VHF. So it's just a little
Ooh,
interesting.
cosmic rays. And then the void. I love that.
So sometimes people give something with a smaller wavelength than 10 to the negative 10th the term cosmic rays, but most people just refer to them as gamma rays. Like gamma is the last one, and it doesn't really extend out, but cosmic sometimes gets used.
So where are all the places that we can experience gamma rays? Because like I know ultraviolet and I know X-rays, but
Space.
just space.
The gamma rays interact with the atmosphere and don't make it to us.
Where do they come from? Like,
All celestial bodies that emit radiation emit gamma.
our sun emits gamma too.
That is a celestial body that emits radiation.
Yeah.
That's the biggest source of gamma radiation for us is the sun, our sun. But
And then didn't you also say like explosions, like big enough explosions?
well, anything that you can see that isn't a sun is an explosion. So all of those things would produce gamma rays as well. So like a black hole formation, pulsar. Pulsar would be probably the worst.
Is there a way to like generate gamma rays through electrical means?
Absolutely, we can totally generate gamma rays. In the same way that we generate we use electricity to generate wavelengths for microwaves. You just change the coil. So the coil is wound a certain tightness, and the tighter you make the coil, the smaller the wavelength of radiation that you generate is. I mean, that's how radio waves work, right? I don't know if you've seen like an old style radio, but it's just a coil that they run electricity through and pulse the electricity to a certain frequency, and then that produces sound. And that thing can be picked up by another coil of the same size, which is why you can't pick up FM radio on an AM radio band because you're not in the correct band to realize that particular frequency. But if you make the coil super small and run electricity through it, you create gamma. Absolutely. One other thing I forgot to talk about with microwave that I thought was kind of interesting is the military designed a break up large groups weapon based around microwaves. Has anybody seen this? The video's been on YouTube a couple of times. So it basically just looks like a truck with a weird satellite dish on it, and then they just point it at the crowd and they turn it on. So imagine what would happen if you jury-rigged your microwave and turned it on and then put your hand inside. Could be bad, right?
Yeah.
So they picked a particular microwave that has really crappy penetrating power, but so it gets down into just the layer where the nerve cells are in your skin. And then it heats that water up.
Oh.
So what I'm told is it feels like there are ants underneath my skin.
Ew.
So that's a problem and it's painful, but the worst part about it is you can't see.
That is.
It messes up your vision. But then they turn it off and or you remove yourself from the microwave and you're fine. There's
That doesn't sound very
zero
ethical.
lasting effect. Is it more or less ethical than tear gas?
Oh.
I mean, there was a guy in Hong Kong over last fall that died because a tear gas canister hit him in the chest and killed him. That
More
can't
than
happen
that,
with
if
this.
it's because there have been cases they literally shoot them down from bridges, and those things are big, heavy, and hot.
Right. What? What do you want? There's green spiders outside?
No.
Oh, you killed them? Okay, great.
Oh no, poor spiders.
Gauge gross. Ugh.
What?
All right, you can go away.
Spiders are.
Rob, would it be
They're
possible
cute,
to
right,
use
Madeline?
other
I could
frequencies
sell
through
them
that
my
dish?
dinner,
Spiders are.
and then
Sure.
I saw them. I
Because
didn't.
I thought I saw a video of someone using those and acoustic frequencies to break watermelons, but I'm not sure if it was the same kind of hack.
It could be. That could work. One other thing is these microwaves. Oh, we talked about that. Sorry. Go ahead. Did you have something else to add to that?
No, I was just curious if it was the same tech, because that's bizarre.
Essentially, yes. The other term that's associated with waves is amplitude. It's not really an issue. Amplitude with waves of light just mean more of them. It's not like the wave is going to go. It's not like it's going to be higher wave as opposed to a smaller wave. It's just the number of waves. That's what amplitude means for light and radiation in general. Okay, so a couple of calculations to talk about with this. This is the speed of light. I'm just going to write it as 3 times 10 to the 8th meters per second. And this is the c that's in E equals mc squared. So the equation to switch between frequencies and wavelengths is just based around the speed of light. So the speed of light will always be equal to the frequency of the radiation times the wavelength of the radiation. So if you know one, you'll know you can calculate the other because c is a constant. So these two things are always going to be inverse each other. If the wavelengths are shorter, then the frequency goes up, and vice versa. So here's a let's do a calculation here where radar waves are a centimeter, okay? There are some radar waves that are 1 centimeter in their wavelength length. So I could plug in the speed of light for C. The wavelength is 1 centimeter, and then I'm going to solve for nu, which is frequency. So frequency is equal, the problem is I got meters here, and I've got centimeters, so I have to convert the centimeters into meters or vice versa. And so then we end up with a frequency of basically 3 times 10 to the 10th hertz. And a hertz is equal to 1 divided by seconds. The other way to write 1 divided by seconds is seconds to the negative 1. But this HZ thing was developed because people didn't want to write 1 divided by seconds. I didn't want to write 1 to the negative 1. So hertz got thrown in there. The second equation involves energy. And so if I want to know the energy of a particular wavelength of light, I can use Planck's constant, and this is it. So if I take that 6.626 times 10 to the negative 34 joules times seconds, I can calculate the energy based off of either straight frequency or using the speed of light and the wavelength to get that. So first off, times 10 to the negative 34th. Somebody want to talk about that number?
Very small.
It's really small, right? I mean, a mole is times 10 to the 23rd, and that's really big. And this is times 10 to the negative 34th. So this is a ridiculously small constant, which is
Planck.
Max Planck, or Planck, is a German physicist who came up with the idea that energy is quantized. So he started the quantum mechanics movement, and we'll be talking about that most likely today.
Will we be talking about the ultraviolet catastrophe at all? What's a beautiful little math thing?
No, I mean, I'm just going to mention the ultraviolet catastrophe, but we're not going to go into what that constitutes, because that's really a PChem class, because you'll spend a month talking about it, doing all the calculations. But this thing that Sheen is talking about, which is the ultraviolet catastrophe, is classical physics tried to describe what would happen with energies and frequencies. And when they do, it deviates from real life dramatically, where the curve goes basically to infinite in classical, and in quantum mechanics, it comes back down to normal and to what's observed. And the only way to get that to happen was to treat light as if it were chunks of energy. But we'll have that discussion here in a sec. So if I know something's, so let's say I know the frequency is 1.2 times 10 to the 15th hertz. All right, great. So I take Planck's constant, I multiply by that number, and I get this number. So how much energy is that? 7.5.
Not a lot.
It's ridiculously small. How much energy is a joule? It
It
takes 4.184 joules to equal 1 calorie. Not this calorie, lowercase c calorie. So 2,500 uppercase C calorie diet is a normal human's diet, probably 3,000 for most Americans. And this is 1,000 times less than that. And this is 4.184 times less than that. So a joule itself is a tiny amount of energy. And this is times 10 to the negative 19th of a tiny amount of energy. So a single photon, a single wavelength of light that hits you is going to have a very, very small amount of energy. And then I'm just gonna let you guys do the algebra on the if you're given wavelength or vice versa. So we'll probably do that for the homework. All right, so we're gonna talk about light acting like a wave. Okay, and by wave, I mean what you think of, like a wave in the water. Like you're in the swimming pool and you use your arm to go up just underneath the water and you produce a wave, or you're at the beach and you get hit with a wave. We're talking about an actual wave. Okay, so why do we think light acts like a wave? Well, it's got some properties that are equivalent to waves. One of them is, and we're also talking about the analogy, or not the analogy, but this also refers to the way sound waves work. So refraction and interference are two of the things that are important to us. So what do we know what refraction is?
Whenever light bounces off something.
It doesn't bounce, it bends. It is turned.
Like I remember whenever someone like you have a striped background and then you put a water in front of it,
Sure.
and then it inverts. Oh, the first one I was thinking was reflection.
Okay, so this happens with light. You okay with that? Light goes through a prism and it separates out. There's probably a decent chance, certainly a decent chance, that somebody saw a rainbow today. Same situation. So it's going through this clear, colorless substance, and when it does, it turns. So what refraction is as the light passes through from a substance of one density into a substance of a different density, it turns. If it passes again through another substance of differing density, it turns again based off of its wavelength. So a wavelength of red turns at a different angle than a wavelength of orange. Red turns less than orange does. Purple turns the most, which is why you see the rainbow over here on the right space out in the way that it does. So the purple frequencies, or the purple wavelengths, turn the most, and so I get this spread pattern, which is white light is, all the different colors of the rainbow. So anytime radiation passes through a substance of one density into another density, if it can break through that, then you get refraction occurring. So besides rainbows, can somebody else give me an instance where refraction is occurring?
Magnifying glasses?
The straw in the water.
Magnifying glass, sure. Straw in water, or this pencil in water. I mean, that pencil is not broken, right?
Yep.
How about when you're standing in a swimming pool and you look down at your feet and they're not right below you? You know
Yeah.
they're right below you. So the light is going and the light is hitting your feet, and then as it comes out of the water, the light bends, it refracts, and then that displaces its actual position. So this makes some particular skill very difficult. What is it?
Underwater.
Fishing. Spear fishing. We okay with
Oh.
that? So if you're spear fishing, that fish is actually offset by a certain number of inches depending on how far it is away from you and the density of the water. How do real good spear fishermen spear fish?
Don't they wait, they see where the fish is and then they stab a little bit forward?
Nope.
They wait till it's closer to the surface so it's less offset?
Nope. They put the spear in the water. So all these movies or TV shows where you see the person with the spear like this and then they slam the spear into the water and they pull a fish out, BS. That doesn't happen. That's not the way it works. You put the spear in the water, and why does that help you? Because the fish
Because
is
then
offset
You know where your spear is.
and the spear is offset. So you don't worry about you worry about the fish in relationship to your spear. And that's how you
So
catch
they-
them.
They
So
barely put it in the water, and then when they see a fish come by, they stab it down.
doesn't matter. However they want to do it. Depends on the depth. But as long as the spear head is underneath the water, you're fine. So any of you get trapped on a desert island and end up surviving, you're welcome.
Oh, I remember one day my chemistry teacher told me this.
Right. And then you'll make yourself a
A fish
spear
raise.
and have fish forever. Probably really good fish. Okay, so this happens in one other instance that is very common to us. Wait, what are you doing? Oh, thank you. All right, you can get out now.
No, Mama's trying to get me.
Yeah, I don't believe that for a second.
No, she is.
I don't believe that for a second.
Yeah. She
I
is.
don't know how to spell this. Imagine that. There we go. So is this actually the end of the flat Earth? Like, is that what's happening right here? Like the Earth ended, like we finally found, and we're gonna fall off the end here, and as we fall down, we're gonna see the turtle that the Earth has been on the whole time.
Well,
Of course.
the Earth is flat,
100%.
so
So what's happening here?
The heat waves are like doing the refraction thing, maybe.
Okay, so heat waves. I don't see any heat there.
I do.
No, you don't.
Well, whenever I
You
'cause
see-
I've gone
you
on a
see
couple
road.
road trips.
You see blue sky. You see some, I don't know, rocks and some sand and some bushes. So you don't
is
see
it
heat.
refracting the sky onto the road
Well, why can't? Hold up a second. Why can you not see the heat?
because it's not visible light.
Right. Correct. So what's happening is, you're correct in thinking that that road is hot. Okay. So great. So the air right above the road, that's basically in contact with the road. What's happening to it?
It's being heated up.
Okay. So when something gets hot, what happened to it? What happens to it?
Convection.
Before that,
Okay.
Molecules start moving extra fast.
they're moving faster, and then what happens to it?
They
Density
break apart.
changes.
The density changes because it expands, right? I heat something up and it expands. So the air right above the surface is actually expanding because it's moving faster. So its density goes down, right? And then we have what Ethan said, which is a convection effect where that less dense air starts to travel up. And so then the air, so that air leaves and new air takes its place and that gets warm. So you have this weird chaotic effect of different temperature air as you're moving above the top of the road. And what is the light on the other side of that hot road trying to do? It's hitting something and it's trying to get to your retina. But on the way to your retina, what happens to it?
It gets refracted.
How, like 1,000 million billion times. So it turns and then it hits something of a slightly different air density and it turns a little bit and turns again and turns again and just keeps doing that like a pinball. And by the time it gets to you, the image that it should be conveying has been mixed up, has been confused. You
That's
okay with
really
that?
interesting. I always
I
thought it
agree
looked
with you.
like. I always thought it kind of looked like water on the road when I was younger.
Sure, that's why people walk towards a mirage like this one here.
Ah,
That really looks like there's a lake there, right?
yeah,
But there's definitely no lake there.
or at least a puddle.
At least something I can drink out of. Okay, so light refracts. Everybody okay with that?
Yep.
Okay, so then let's talk about interference. Okay, so interference comes in two flavors: constructive interference and destructive interference. And so constructive interference adds the waves together to make a bigger wave, and destructive interference subtracts them to make a smaller wave, or maybe cancel the wave out completely. We okay with that?
So it compresses the light.
No, they literally, if you think about it as far as ocean waves go, let's say one wave is going up, at the same time it runs into another wave that's going down.
And
And then they cancel each other out and the thing becomes flat.
Okay.
So the wave that's going higher than the surface of the water, there's a hole there. And so it falls into the hole and then the whole thing becomes flat. You okay with that?
Yeah.
So this happens. And this happens with light. So this image over here, this pink image. So what we have here is Penelope, get out of there. Hey, get out of there right now. Yes. Go that way. Yes.
Mom's trying to get.
Just a second. Actually, you know what? I'm going to give you 5 minutes. Because I'm going to take 5.
Okay. Nice.
You.
This chapter is really confusing. Like, I'm getting the concepts, but I'm afraid that, like, when the test comes by, it's just gonna be absolutely, like, I'm gonna be blindsided again. I'm gonna get a snack. Does anyone want a snack?
No, you want to see a useless achievement that I've achieved over the quarantine?
Sure.
This
Hold
is
on.
a old
Hold on.
gas gauge.
I can't see your camera. Hold on. I'll just do the grid. Where are you,
Old
she?
gas gauge.
God damn it, you moved. What's it for?
It was originally connected to a gas pump that started at 23,000.
Have you just been winding it down?
If I'm not winding it, I hand it to someone else to like, yeah.
That's horrible.
I mean, the things we do when we have nowhere to go and, well, no free time, just idle hands.
I started learning Chinese, and the only words I have down
Good
are
afternoon, don't walk the freaking door.
1, 3, and 8.
Okay.
That's it. That's all I got. That's my quarantine achievement.
Anybody else got anything they want to share?
My quarantine achievement is not dying.
Oh, speaking of not dying quarantine achievements, I have one more. I made my lizard a giant home.
Nice.
Oh my god, that's just precious.
Thank you so much. She has like a rock garden and a vegetable garden and an aloe that she can totally mutilate.
Amazing. I wish I could see it, but I'm in my kitchen right now.
Yeah, my plans when not doing classwork have included playing video games. That's
See, I've tried to play video games, but like I'm too lazy to play video games at this point.
yeah, because you have no one to play them with anymore.
No,
Just
man,
wanna
that's
play-
not true. That's
Just
so
want to go play
mean.
Minecraft? You want to just go play Minecraft, and you
Yes, I
can't.
sometimes play Minecraft alone.
I don't know. Do any of you do redstone if you do play Minecraft?
No, redstone is too hard.
It's not too hard. I don't know what you're talking
Even I don't want to hear it. Okay.
I've been using it.
I want to hear you negatively.
Also, speaking of light doing terrible damage, here's a terrifying video of someone creating a handheld 100-watt laser.
So lasers are a thing now?
Lasers have been a thing for a very long time. The thing about this laser is it's just there's no reason for it to exist. It's too powerful. It's
I copied and pasted the link so I can watch it after.
oh god. It's hard to know the scale with lasers because like you're thinking in watts, but like the handheld laser pointer you're used to thinking is like 100th of a watt. This thing is terrifying.
Sounds fun.
He can sear steak with it if it's any like very like nigh instantly. Just you point it at a steak and it becomes black, and like the first 2 millimeters, and then the rest of it just gets warm because it just burns it that fast. And that's without a lens to focus it. It's terrifying.
I gave you 3 things. Eat those.
No, it hasn't been 5 minutes. I'm making my bagel. Oh, 2 minutes maybe.
It's been 5 minutes exactly.
I have to butter my bagel or to cream cheese my bagel. Also, my headphones are glitching out bad. Ow, ow. What was Penelope doing, anyways?
She was messing around with the cables that plug my mouse and keyboard into the computer.
Troublesome.
Yeah. Okay. So, if you take a flashlight and you put a piece of duct tape over the flashlight,
Mhm.
and then you take a really, really sharp knife and you draw or cut a slit into it, and then you shine it at a wall, you don't get what you expect. And more interestingly, if you take put two parallel slits next to each other, very parallel slits, thin slits, and shine it at the wall, you get something that you wholeheartedly would not expect at all. And anybody can do this. Super sharp knife, duct tape, and a flashlight, and then darkness, shine it at a white wall, and you will see something that doesn't make sense to you. And except it will, because we're going to talk about it. Okay, so let's do this with analogy first. So many ports or harbors actually have break walls on them, meaning they don't want waves coming in. And the problem about being in port, like when I was the first year that I was on the aircraft carrier, a tropical storm was about to turn into a hurricane, and it had a stupid name like Hurricane Bob or something like that. But our boat was on the pier, and when we found out that it was going to hit Norfolk, our captain called everybody in, and we went out to sea. So the hurricane's coming, and he took us out to sea. Does anybody know why?
Were you taken to a more stable place?
No, we literally went right through the hurricane because he thought it was funny.
Oh.
It actually was kind of funny.
Well, aren't they like super strong ships because you have to endure like really big waves?
Yeah, but it doesn't work if you're next to a concrete pier. So what you're worried about is the boat getting slammed against the pier. So
Okay.
during really bad storms, big boats leave and they go out because there isn't anything for them to run into, and they're not worried about sinking.
Well, what about like tiny sailboats?
They sometimes just pull them out of the water.
Oh,
Wow.
So they'll put these break walls in to make sure that big waves don't make it to where the boats are moored, harbored. And so if there's one of these, you'll end up seeing this interesting pattern where as the water enters this, maybe I should pick a different color. When the water enters this, instead of it just like coming straight through like this, as it comes out of the opening, it arcs. So it spreads out in exactly the same way that when a rock hits the water, it forms a ripple. So when you try to send something through this hole, a half ripple is formed. Okay? So that causes a wave to come out in an arc the entire time, out to wherever it goes. Usually when they put these break walls in, they put two break walls in, two openings in the break wall. One is basically like you go in this direction, you come out this direction. You okay with that? So when they first started doing this, what they noticed was some sections of the harbor were very, very calm, even during the worst storms. And then other sections of the harbor, the boat that was moored there was destroyed. So what's happening? Well, what we're trying to show here is as these waves, what would be a good color? As these waves arc out, they will intersect with the waves coming out of this. So when these waves come out and these waves come out, they're going to run into each other. And sometimes when they run into each other, both waves are going up at the same time. So then what's going to happen with the new wave that's formed?
does it just make a bigger wave?
It just makes a bigger wave. But what happens when one of them's going up and one of them's going down?
It evens it out.
It cancels it out. So when they cancel each other out, that's called destructive interference. And when they build up on top of each other, that's called constructive interference. In marine life, you do not want constructive interference. That's a bad thing. When you're walking down the beach, is the walk along the water a straight shot?
No.
What do you find yourself doing?
Weaving.
You're going in and out. Why? Well, there's hard objects underneath the water that cause this same effect to occur. And so the waves naturally produce constructive and destructive interference points. There's a destructive interference point on the coast of Oregon. Does anybody know where it is? The biggest one?
Oregon.
Somebody tell me where it is.
Is it on
For the little dippers?
What'd you
is
say,
it at the
Kalina?
super windy beach at Cannon Beach?
Kalina, what'd you say?
Where the little dippers?
Dip? It's I don't know if I can do that here. Let me do this. It's that spot right there. Can
Oh.
you guys see that thing I circled?
Yeah, the little bump.
Why is that the most destructive interference spot on the entire coast?
Because the waves are coming in from each side of the bump, and then they meet in the middle and make a bigger wave.
No, they cancel out destructive interference, which is
Oh.
why that portion of the coast has been eroded the least. So the portion that's pushed in the furthest, like harbors and bays, those are constructive interference spots that the waves just kept pounding on one spot on the coastline and kept pushing in, pushing in, pushing in. Does that make sense?
Mhm.
So when you're walking along the beach, if you're wanting to buy beachfront property, some of the properties will be significantly less than other properties, and they won't be very far away from each other. They'll basically have the same kind of view, and everything seems to be the same, but what's different about it?
The waves.
The waves at that spot on the cheap house, that house had to be reinforced or hasn't yet been reinforced because that's the point where the waves keep hitting. And the house that's 10 houses down the road that's more expensive, that's a destructive interference spot. And so you know that coastline right there is going to be stable. That makes sense?
Is that why there's some like super long beaches like Cannon Beach where like to get from the road to all the way to where the water is super long?
So that's a
Because
destructive interference spot.
Okay.
The constructive interference spots are like short sands. Like the sand itself, the distance from the sand is a very short amount of space because that's where the water is constructively interferencing with each other, making bigger waves, hitting the ground harder right there. We okay with that? All right, so let's go back over here. So constructive and destructive interference happens with waves. Everybody okay with that? Water waves?
So it happens with light waves too.
So if light acts like a wave, then this would happen, and it does happen. So when you put that double slit on the flashlight and you shine it at a wall, you're going to get a bright spot, dark spot, bright spot, dark spot, bright spot. It's going to fade as you get further away, but you will have these actual spots. You would expect to just see a bright spot right where one cut is and a bright spot where the other cut is, and what you end up having is these bands where constructive and destructive interference is occurring. What is that you linked there, Gene?
Oh, it's a terrifying 100-watt handheld laser.
Okay. Yeah, don't want that.
Yeah, we were having a conversation while you were out about lasers.
Gotcha.
Also, is that principle how those like sunglasses that aren't like polarized or anything, they're just slits works?
No, those are fashion.
Well, no, like the one they have. There's really old ones that are like from Inuit, and like those places near the north where they just have like really thin slits cut like that.
They're like leather blinds.
Is that the thing that you use to look at the sun when you don't have good polarized lenses?
No, that's a layered glass. It's called starts with a G. All right, it'll come to me. Okay, so why is light thought of as behaving like a wave? Give me some reasons.
Because it does.
Because it does, flat out, right? We see the actual results that we have constructive and destructive interference, just like what regular water waves. We also see refraction that happens with regular regular waves, and so this is behaving just like them. The same kind of situation can happen with sound waves. Right across the street from the engineering building at Oregon State, there used to be some guys who had a company that they would come out to your house and set up your sound system in your house. And what they would do is they would say, okay, your couch is here and your TV is here, and you want it to be loud right here on the couch, but you don't really want it to be loud anyplace else. So they would set up some spots in your house to make it so it sounded really good in some places, and other places it sounded really bad on purpose. And the way that they got everybody to buy in so they could do what they were saying they could do is inside their studio, they had a big stereo system, and they gave a person a remote control, and there were two X's on the ground. One was blue and one was red. And they said, okay, turn it on. They gave them full access to the stereo, and they said, turn it up to like 2, and then stand on the blue. And when they stood on the blue X, it actually sounded like they turned the volume up a lot, even though no volume change happened. And then when they stood on the red X, they could almost not hear anything. They were only like 5 feet away from each other. So what you didn't see is behind the curtain, they had the speakers directed in interesting angles. So they're not just pointing directly at the person. They were like pointing backwards at the wall, and it would ricochet off of the wall and come down to a certain spot. And depending on how they angled those things, they could get constructive and destructive interference. So what they would have is people that worked at the university and people that worked at HP that had money, they would bring these people in and say, we want to watch TV right here. And we want to put our sleeping 1-year-old right here. Make it happen. And so they would set the sound system up so this spot that was a couple of feet away from the couch made no noise. So they could be listening to a loud explosions, gunshot action movie. Baby doesn't hear anything. You can see this effect happen in person if you go to Portland. I feel like maybe we had this conversation, but I can't remember if we did or not. Did we? About the amphitheater?
We did at the amphitheater.
Okay, so that amphitheater is constructive and destructive interference. That's exactly the same thing that's happening. So light does this. Okay, so is everybody in agreement? Everybody okay with the fact that light actually is a wave?
Yes.
Okay, so now light is not a wave. Yeah, sorry, but it's not. Except when it is, but it's not.
God, I swear.
I can't change nature. Okay, so Einstein didn't actually win his Nobel Prize for theory of relativity. He just got more notoriety for it. He won his Nobel Prize for something called the photoelectric effect. And the photoelectric effect is work that Planck did and Einstein did. And the issue was you could not explain what was going on unless the photoelectric effect was occurring. Okay, so great. What's photoelectric effect? So they called it the photoelectric effect because photo equaled light and electric equaled light electron. So everybody okay with solar panels? Whether it be on a tiny calculator or be on top of a house?
I mean, I'm okay with them, but what do you mean?
Just the concept that you hit this panel with light and electricity is generated.
Yes.
Okay, so basically what I have is a metal, and light hits the metal. The electron gets ejected out of the metal and run down a conductor through the house, heats up your hot water heater, does whatever it does, runs the lights. But regardless, I have light come in and hit this thing, and this electron gets ejected off of the metal and sent through the circuit. Okay, so here's the issue. I keep doing that.
Could you have your own light source and have it power?
Yeah, but then you'd have to power the light source.
Yeah, just use your neighbor's outlet.
What? Why wouldn't I just
No.
plug whatever it is that I'm trying to power into their outlet if I'm going to steal outlet electricity. That's like a roundabout way to get what you want. Okay, so
Do everything.
this red light hits the metal and nothing happens. But the green light, when it hit the metal, caused the electron to leave. So why would that be the
Because it has
case?
more energy.
Okay, so red has the least energy in the visible spectrum. We okay with that?
Yeah.
And
Yeah.
green has significantly more, so it has enough energy to do that. So okay, so great. So what would happen if I took, instead of just one small red light, I made a bigger red light? So maybe the light that I'm shooting at this is a really big light bulb, and I'm shining it down at my little solar power calculator. What's going to happen? So I take a tiny light. I take a tiny little flashlight pen like this thing right here, and I shine it at the calculator, but it's blue light. And I take this. Have we seen these things before?
Mm-hmm.
These infrared lamps. This is just like basically a heat source to keep that meat at the proper temperature so bacteria can't get on it and like kill people who are at the wedding or at the buffet or whatever's going on.
Mm-hmm.
So that lamp is producing a lot of energy and hitting that piece of ham in this case with so much energy that the bacteria can't live on top of it. So a lot of energy. You are not going to keep that ham warm with this tiny little pen flashlight, but you're definitely going to keep it warm with this. You cannot keep your hand underneath this light for very long without it burning you. Okay? So let's say that I take this lamp right here and I shine it at my calculator. It's a super powerful light. So what's going to happen?
You can bust your calculator.
No, calculator isn't going to break.
Then I guess you would get a fully charged battery.
You get nothing. You get absolutely nothing. Even though I'm throwing untold billions and billions more actual radiation in the form of red light at this calculator, nothing happens. But then I turn this tiny AAA battery pen flashlight at the calculator, and the calculator blank turns on immediately. So what's the problem?
The light source is producing heat, but not as much energy as the calculator needs, while the blue one is producing more energy, but not a lot of heat.
It doesn't have anything to do with heat.
Well, I'm saying that the reason why the top one is useful is because of its heat, not because of its energy.
Heat and energy are the same thing.
I know.
Does anybody have a reason behind this?
It's the wavelength of the light, right?
Okay, so what about it?
It's a higher frequency, so it's got enough energy to pick up electrons.
Well, those 4 red wavelengths of light that I just showed right there in this little image, you seeing those? Together, those 4 have almost 3 times as much energy as that green light.
They have a specific amount of energy. The green light does.
True, but that's not important. How about this? You want to move a refrigerator.
Mm-hmm.
Okay. So you call some people, you get a hold of some people, and some people show up. And the people that show up at your house is an entire classroom of 3rd graders.
Yes.
And 2 guys that play offensive line for the high school football team. So if I gave a test to these 2 groups and said, pick up these rocks, the football players could pick up the same amount of rocks as far as weight goes as the 3rd graders. We okay with that? So each 3rd grader can pick up 40 pounds, and the football players are each picking up 200 pounds of rocks. But together, the 3rd graders are also picking up 400 pounds of rocks. So it's equal. So I can pick either group, right?
Mm-hmm.
No, I can't. Why are you saying yes? Why am I not able to pick either group? I still have to pick the 2 football players. Why?
Because it's less people.
No,
Child labor laws.
no. can you get 30 third graders around a
Oh.
refrigerator and interacting with the refrigerator at the same time?
They would no.
No.
They would be too
Well,
hyper.
maybe if they work like ants, like maybe if you lay it on top of them.
You still can't get 30 of them underneath it. So even if I pack them all super tight together and then drop the refrigerator on top of them, I still don't have all 30 of them, right? It's still maybe 12. So 12 dead kids and 18 kids are like, damn, I'm glad I wasn't underneath there.
Just use the corpses.
Well, I just
Like,
lost.
Use them like.
I just
rockets
lost
and
45% of my lifting power because I killed them, so it doesn't work out. So what's the problem here? All right, let me stop for 1 sec. Let's do something else. Fine. This one's totally fine. So tab, blah, blah, blah. So are we okay with me saying that it's going to take a certain amount of energy for you to walk up this step? Okay? You got to pick your foot up and you got to set it on the next step. Okay? So let's say, I'm just going to make up something. Let's say that it's 5 calories to do that. Okay? Everybody all right with that? Well, I don't want to do that. I don't want to exert 5 calories of energy. So instead of exerting 5 calories of energy, what I'm going to do is I'm going to exert 2.5 calories of energy 3 times. So that's 7.5 calories of energy. So I'm exerting more energy than the 5 needed to get up the step. Have I taken a step yet? No. If you pick your foot up halfway up a step and then set it down and do that 3 times, you will not be able to clear the step. Does that make sense? So what we're doing here is we quantified the energy in units of 2.5. And 2.5 isn't enough because I can't add 2.5 and 2.5 and 2.5 and get to 7.5. I only get 2.5 units of energy. So how does that apply to this thing? How does that apply to this?
The green energy has more energy per waveform.
Okay, true. We already said that though.
It's more efficient.
No,
It's the correct amount of energy?
no, because blue would also lift this. Purple would also lift this. UV would also lift this. I am not allowed to add the red lights together to make a bigger energy in the same way that taking those 30 third graders, that I can't put them all together.
Because they're too big?
No, because you're not allowed to. In the same, 30 third graders cannot pick up a refrigerator because 30 third graders can't access the refrigerator all at the same time. So what I'm saying is, even though those 4 wavelengths of red light are more than enough energy to eject an electron, the electron will only allow one of those wavelengths to interact with it at a time.
Oh, okay.
So the first red hits it and the electron says, nope, not enough. Then the next one hits it, nope, not enough. Nope, not
So it's
enough.
just
Nope,
one at
not
a
enough.
time.
It's one at a time. And what's the term for that?
Oh.
So energy is quantized.
So that would be like if each third grader tried to pick it up one at a time.
Yes.
Okay.
Or you paired up the third graders and said, all right, you two, go pick that thing up. No, it's not moving. We okay with that?
Yeah.
Okay,
See, I
so
thought you were talking about the red light interacting with the whole piece of metal, not just one electron at a time.
well, that's pretty much what he's saying, that when you interact on and perform this photoelectric effect, only one electron is allowed to be interacted with at a time. So this is digital. This is analog. What's the difference?
One's continuous and one's discrete.
Okay, so what do you mean by discrete? You're correct.
It's like if it's Boolean, then it's 1 and 0, and that's it. Like there's no in between states.
Sure. So if you're listening to music on an album, which I don't know how many of you actually have albums, but regardless, that's
Metallica.
what does Metallica have to do with albums? Oh, because
Oh,
they
I just
release-
have a bunch of Metallica albums for the car.
What? You have a bunch of Metallica albums for your car? Is that what you just said?
Like DVDs.
No. Album. Like that thing Gage just pull one out.
Oh, you mean like a
An album. The thing that
A
I said.
record.
A record, album, same thing. So that piece of vinyl right there has all of the information from a musical session recorded on it. Okay? And so the way that it works is it's called cutting the record. When they first cut the record, they have this very flat piece of vinyl on it with no imperfections on it. And they run a needle over the top of it that actually is a knife. It cuts into the surface. So, like if you have a glass of water on the table and you yell at the glass, what happens to the surface of the water?
it ripples.
It ripples. So you had an impact. So what would happen if I had this very pristine vinyl record with a knife on top of it and the record was moving and I yelled at the needle and the record?
You would imbalance it.
I would cut into it. And then if I then took that cut album and put a different kind of needle on it, it would actually play back the yell that I put back on, that I yelled to make that indentation. And that's how records worked. So when a person would be singing, playing a guitar, playing a piano, there'd be crackling and popping background noises kind of stuff. All of that would get recorded on it, and all of the information is on the record. So then we go over to Annika's DVD players or any of your phones that have any sounds on them, like the ringtone or any music, and it's different. And the difference is it's like this. So this is digital. So what's happening here?
It uses different measurements at specific points.
I don't know what that means. What it does is it records a segment of the sound being generated, and then another segment of the sound, and then another segment of the sound. So what's the obvious bad part about this?
Is it lower resolution?
Well, what about this thing right here that I'm circling? What did that sound like? While they were playing that song, what did that spot right there sound like? Don't know. I didn't record it. Is that a problem? Maybe. Why is it not really a problem? Are any of you, when you listen to music on your phone or music that comes from your phone and goes through your car stereo, or if you're streaming something, are you upset about the sound quality? Do you hear like gaps in the music or the dialogue? Why not? The gaps are
Because
too
they
close
edited?
together.
You
No.
can't tell.
You can't tell because the gaps that are there are too close together. I mean, when you're watching a movie on Netflix, technically, what are you seeing?
You're seeing a frame rate.
What do you mean by a frame rate?
You're seeing, I don't know, 40 frames per second.
What do you mean by 40 frames per second?
You're seeing 40 different images per
Awesome.
second.
Sorry, we're gonna get this stupid because I have the wrong. Whatever, doesn't matter. Anybody need some South Beach diet?
Yeah.
Actually, you know what? That's not a terrible idea right now because don't they deliver the food to your house? Yeah,
Yes.
I don't have to go anywhere. Okay, so skip, go away. Why isn't this?
But this makes me like this makes me ask. I have music recording software and it renders at 44,000 hertz.
Yeah, that's terrible. Okay, so we'll talk about that in a second. So here's a flip book. What are these things?
Pictures.
Individual framed pictures, right?
Yep.
You do not get to see actual motion, right? But your brain perceives this as motion, even though what you're getting is a picture, and then there's a gap of information that you missed. So when this guy gets sucked up into the spaceship, a portion of the time frame where he's being sucked up, like he moves like, I don't know, a couple of millimeters. You missed that. But your brain doesn't really care if that's going fast enough. Or if the pictures are drawn where instead of him moving 2 millimeters, he moves a tenth of a millimeter, and they just end up doing 200 more images. Does that make sense? So the old Disney movies, they would draw a boatload of cartoon panels, right? And then just put them right next to each other. That's digital. Digital means I'm looking at individual things and there's gaps in between them. So let's go back to what Ethan was asking about. So let's say that this is this digital that I have here in purple, that's the 44 hertz that Ethan is talking about. Well,
44,000.
yeah, 44 kilohertz. So 44 kilohertz is what talk is recorded at. Music is recorded at a couple
I can
of
set it
couple
to
of million
192.
couple of million kilohertz. If you're looking at taking like a song off of a DVD, like how many songs fit on a CD? Like you guys know this kind of information, right?
It's like 15.
Yeah, like 15 will fit on a CD. And the reason only 15 fit on the CD is because this is what it looks like. So how big are the gaps between the music? You can see me drawing these ridiculously small green dots, right?
Very close together.
So the gap is very small. But the problem with that is it takes up a lot more storage space, right? So what if I rip a CD and turn it into an MP3 and I make the spaces like this? Well, now I can fit like 1,000 songs on a CD player, on a CD. And the quality's gone down. So at some point you're going to hear, it's not going to sound as great to you. Like this music that you're listening to doesn't sound good at 44 kilohertz, but it sounds pretty good at 128, sounds great at 256. And if you're at 1028, like awesome. Like that basically sounds like an analog record. We okay with that? So the closer those get to each other, the less like digital it looks. So televisions today, like have you all experienced a VCR?
Nope.
When you pause a tape,
Yes.
a VCR tape, the image that you're looking at during the pause is kind of a smear.
Mm-hmm.
If you pause Netflix, say you're watching, I don't know, Infinity Wars on Netflix, when you pause it, what do you see? A crystal clear image.
Yeah.
That's because the pictures that they took were closer together. So instead of it being, when TV first came out, they did 15 pictures per second. Then they upped it to 30, then to 60. And then finally they hit 120 and 240. And now I don't even know what it is at. It's probably somewhere around 500. So that's 500 pictures per second. So is your brain going to be able to see the distance between the 500 pictures per second? No.
No.
And then the other cool thing that your brain does is even here on this one where there's a large gap, instead of your brain hearing a pause, it smears this together. So it anticipates what should be there, even if it's not there. We okay with that? So true audiophiles will pick analog over digital, even to the point where if it's like 10, sorry, if it's like 1028 kilohertz, you can't. If I played that and played the record, you'd have almost, there'd be no ability for you to tell the difference between the 10, 20 kilohertz and the analog record. But if it was 128 kilohertz and a record, somebody who's heard that record a lot, heard that song a lot, could say that one's missing something. It sounds a little more hollow. So radio stations are broadcasting at 128 kilohertz, and talk radio or podcast will be sending it out at 44, which is why you can put like a billion podcasts on your phone, because the kilohertz rate is really small. But if you start jacking up the kilohertz rate to something like this, then, I mean, you can see that this is 10 times bigger than this guy. So I cut my amount of songs down by a factor, an order of magnitude. Okay, so what's this have to do with what we're talking about? The issue is, we said up here that light acts like a wave. But when a wave comes in off the ocean and you get hit by it, do you get hit by a little bit of water and then a gap and a little bit of water and a gap? No, it's just one continuous thing. When you sing a note, it's not like there's some music, there's a tone and then nothing, and a tone and nothing. It's all continuous, and that's what waves do. But unfortunately, light only behaves like a wave sometimes, and sometimes it doesn't behave like a wave. It behaves under this photoelectric effect. So when I look at it in one instance, it's a wave, and when I look at it in another instance, it's a quanta or a packet. So we can say that this is a small packet of energy instead of a continuous amount of energy. That's called a quanta, and then the other term for it is a photon. So the light that's hitting you is hitting you in small, tiny packets of energy. And if I'm using a solar panel, those small packets of energy might be enough to eject the electrons out and cause this to, to generate electricity for me. The next thing I want to talk about is atomic line spectra, but it's kind of a big topic, so I think I'll just wait until Tuesday. Okay. Does anybody have any questions about what we talked about today?
Are the two calculations that you showed us the first set of calculations that we've been introduced to, or do we have any more that we've already talked about?
I don't know. Do you consider the addition and subtraction that we did on this homework, the homework that we turned in today, as calculations?
Homework that I forgot to do.
Yeah. So, I mean, if you want to consider this right here a calculation, then okay. But otherwise, like these things right here as a calculation. I mean, it is addition, so it is a calculation.
Don't think for screen sharing.
Yeah, you're not screen sharing, Rob.
Damn it. Like, technically, this is a calculation.
Yeah.
So there's our first calculation. And the second calculation will be, say, I've got orange light at 600 nanometers, and I want to know how much energy that is. Tell me. Or tell me what the frequency of that is.
Also, we are only dealing with light, right? We're not dealing with sound.
Oh, yeah, absolutely. Sound has nothing to do with this.
Okay, cool. Because we did talk a lot about it, but.
Okay. Anything else? Anybody? No? Good to go? All right. So July 1st is coming up pretty soon. anything significant about July 1st or June? Sorry, June 1st.
Yeah,
Anything?
that's our paper labs.
All your labs are due on June 1st. And honestly, I've probably got